Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic, layout diagrams using nMOS design. In our previous lecture, we have completed the stick diagram concepts, which has included the significance of stick diagram, why a stick diagram is required, and what is meant by stick diagram exactly, and what are the rules to draw stick diagrams, and few examples based on stick diagrams have been taken in the previous topic. So now for today we will look into the layout diagrams nMOS design. We start with first the design rules and then we check out few examples going into the details. After completion of this lecture you will be able to illustrate the lambda based design rules, and you will be able to develop the layout diagrams using nMOS design. So MOSFET, for your understanding, basically we always start with a MOSFET representation layout where it is represented like this, whereas device structure of a MOSFET, as you know from our past classes, looks like this. So always layout represents the top view representation of the device. So when you check to this layout view, this is our layout view where this coding, color coding, red color coding indicates polysilicon, nothing but gate, and whereas green color indicates diffusion, more clearly to say N diffusion, that is source on one side and drain on other side. So if you compare and learn like this, once you look to the top view of the device, see this part, that is the source, is represented here, whereas this part, that is the drain, is represented here, and whereas this part is represented here as polysilicon. So this overlapping of polysilicon with the diffusion, N diffusion, represents a MOS transistor and nMOS transistor. Hope that is clear. Where this is marked, no, this L represents the length of the channel. So this is our length of the channel that is represented there, and the perpendicular dimensions, that is this dimension, represents the width of the channel, this one. Hope this is clear. Going into the details. So first of all, we need to know what is aspect ratio for pull-up and pull-down transistors in an nMOS circuit. Always the size of a MOSFET depends on the reference inverter design. So here the reference inverter design will be always an nMOS logic design inverter with a depletion mode load. That means what we have seen in our previous classes. nMOS inverter pull down network will be an nMOS transistor in enhancement mode where you will be applying the input, and pull up transistor will be a depletion mode transistor whose gate is connected to the source, short circuited to the source, and here we collect the output. So this one will be the reference inverter always. So what is aspect ratio means? The length to width ratio of a given device is known as aspect ratio. So if that is a pull down device, we call it as ZPD, and if that is a pull up device, we call it as ZPU. So the ratio of aspect ratios of pull up and pull down is known as inverter ratio. ZPU to ZPD is termed as inverter ratio. That is what, whenever we draw a stick diagram, inverter ratio should be mentioned for the gate, so that the designer or the fabricator will understand what is the inverter ratio of the circuit. Next, a few details about aspect ratio. For example, if we say the reference design has a inverter ratio of 4:1, which we have derived in our previous class, ZPU by ZPD ratio. ZPU by ZPD ratio as 4:1 for an nMOS inverter driven through another nMOS inverter, then the ratio of effective ZPU by effective ZPD should be equal to 4:1. So what is this effective ZPD to effective ZPU means? See here, If MOSFETs are connected in series, then effective L by W is nothing but sum of the individual L by W's, that is lengths and widths. So if MOSFETs are connected in series like this. So what is the effective L by W of this configuration is if this is transistor 1 and if this is transistor 2, then that represents L by W1 plus L by W2. Similarly, if MOSFETs are connected in parallel, the effective L by W will be equal. L by W1 will be equal to L by W2. So mostly we have two values of this inverter ratio. One is 4 is to 1 to save the space, that is for an nMOS driven by another nMOS directly, and 8 is to 1 where input is taken from a pass transistor. So between two nMOS inverters we have a pass transistor. So inverter ratios for nMOS gates can be achieved in different ways. For example, an inverter which requires a 4 is to 1 inverter ratio, you can follow two ways. The first way, simpler way, is pull up with 4 is to 1, that is L by W ratio for pull up is 4 is to 1 and L by W ratio for pull down is 1 is to 1. So this is pull up and this is pull down. Putting them together, so what is the pull up to pull down ratio? You can achieve it as 4, or otherwise pull up you can keep it as 2 is to 1 and pull down as 1 is to 2. So what will be the ratio of these two, that is ZPU by ZPD, will be 4 is to 1. Similarly with 8 is to 1 can be achieved in different ways. So if that is an NAND gate to 2 input, in order to achieve 4 is to 1, you have two transistors in the pull down network for an AND gate. Two transistors will be in series configuration. So series means their L by W ratios gets summed up. So in that case, how much is suitable, that much should be taken into consideration. Similarly with a 2 input NOR gate also. Few of the lambda based design rules we will let to know now is developed by Mead and Conway. So all device dimensions are in terms of lambda only represented, where lambda is the minimum feature size of a transistor need to be considered, and which is equivalent to L by 2, where L is the minimum feature size, so L is 2 lambda. So these rules support proportional scaling. So what are the lambda based design rules? Under lambda based design rules, if that is an nMOS design, the minimum feature size, that is active area, would be, as L is 2 lambda and W is 2 lambda, then this would be 4 lambda square, and L by W ratio is 1 is to 1. Whereas for CMOS, as L by W ratio is 1 is to 1.5, that is 2 lambda by 3 lambda, active area would be 6 lambda square. So what are the few design rules? Minimum length or width of a feature on layer is 2 lambda to allow for shape contraction, and minimum separation between the features should be 2 lambda. And then one more important thing here is two features on different mask layers can be misaligned by a maximum of 2 lambda on the wafer. But if that overlap is undesirable, they must be separated by at least lambda. See here pictorially represented design rules for nMOS. Minimum width of polysilicon and diffusion line is 2 lambda. See here this red color coding indicates polysilicon. Minimum width should be 2 lambda, and for diffusion also this should be 2 lambda. Minimum width of a metal line should be 3 lambda, as metal runs over a more uneven surface than other conducting layers. That is what that presentation. Then coming to the spacing between polysilicon and polysilicon, there should be 2 lambda spacing between these two, and between metal and metal the spacing should be 3 lambda between metal and metal. Between diffusion and diffusion the spacing should be 3 lambda. So this one between diffusion and diffusion. And diffusion polysilicon spacing should be lambda. Between diffusion and polysilicon spacing should be lambda. Metal lines can pass over both diffusion and polysilicon without electrical effect. Where no separation is specified, metal lines can overlap or cross. So this is the metal line. This can overlap or cross polysilicon or diffusion without any electrical contact. Metal lines can pass over both diffusion and without electrical effect. This we have seen. It is recommended practice to leave lambda between a metal edge and a polysilicon like this. A separation of lambda should be there. And coming to contacts, metal connects to polysilicon or diffusion by a contact. So if metal, this one needs to be connected to polysilicon or diffusion, that can be done only with the help of a contact. This is the representation of a contact whose area is 2 lambda by 2 lambda. That means on this side this is 2 lambda and on this side this is 2 lambda, and here from here to here this is 4 lambda, means on all the sides it should leave a space of lambda. So these are the design rules that are summarized what we have just now discussed. And see nMOS layout, how it can be represented. So I have taken a graph sheet wantedly. See here, this represents what? This is a polysilicon and this is a diffusion. So both are occupying same number of units on the graph. So that is L by W ratio is 1:1. What is L? Length of the channel. So which is the channel? On this side that is a source and in this side that is a drain. So separation between source and drain is length of the channel L, and its perpendicular dimension, this one will be width. So this is a 1:1 what we say L by W ratio based nMOS, and you can rotate it also. Now see here, source is on this side, drain on this side, and this is the polysilicon. So here what is the length of the channel? This one represents the length of the channel and this represents the width of the channel, 1:1. So if I want to make a 2:1 transistor of L by W ratio, see here, this is the source, this is the drain. So between source and drain, there is a two divisions that have been occupied, right? So this is one and this is one. Together that is 2, whereas this is the width W. Hope that is clear. And see, this representation also a similar representation, but an yellow color encapsulation is marked, that is called as an implant. So whenever there is an implant, we call this one as a depletion mode transistor. And here few more rules are marked. See, between implant and the polysilicon there should be a minimum dimension of separation of 2 lambda. So here also between the contact, that is a metal layer, and polysilicon there should be a separation of 2 lambda. So few examples of the layout diagrams that were given here is the nMOS inverter, so which you can go through with the circuit schematic. You can take the circuit schematic of an nMOS inverter of enhancement mode transistor, and you can verify how this is a color coded layout, and this is the grayscale. This is a grayscale layout. Similarly for nMOS depletion mode load, how the color code and the grayscale has been done. And then nMOS NAND with 2 inputs here and 1 output. If you know the circuit schematic, you can understand the color encoding and the gray code encoding. Then comes nMOS NOR also in similar lines, you can analyze with the circuit schematic. So these are a few lecture level questions which you can try and answer. That's all for this topic. Thank you. Happy learning.